Analytical Chemistry 1, Lesson 26. I prefaced the last lesson by claiming that while a multi-equation chemical equilibrium problem was complex, it was basically just a bunch of algebra. Well, that was perhaps a little cavalier. It doesn't have to include very many reactions before it becomes very difficult to solve. And here is the basic problem. The mass balance and charge balance equations are linear. The various unknowns are added together. The equilibrium expressions, on the other hand, are nonlinear equations. Terms with different unknowns are multiplied together. Chemical equilibria involve solving a set of simultaneous nonlinear equations. And this is much more challenging. Yes, it can be solved, and there are software packages out there where a chemist can just enter her set of equations and let it chug away to find solutions. But they are quite specialized. For most of your work in your career, you will want to tackle equilibrium problems more casually and more quickly to find good enough answers. In this video, we will look at the ways to apply approximations to solve these problems in a more straightforward manner. Look at some of the problems we've completed rigorously so far. Start with a simple solution of a strong acid, HCl. We have the dissociation of the HCl and, being an aqueous solution, we note the autoionization of water as well. The mass balance and charge balance equations can be written down. The equilibrium expressions are here. We make approximations that are informed by our chemical knowledge and experience. Now, they're not just wild guesses. We can make wrong assumptions, so we have to check things at the end to make sure. First thing our chemical knowledge tells us is that the HCl is a strong acid in water. It is essentially fully ionized or dissociated. We do not expect to be able to measure HCl at all. Our first assumption, therefore, is that the HCl concentration is virtually zero. So we set HCl concentration equal to zero throughout our equations. That simplifies the mass balance so that change can carry over into the charge balance equation. Having assigned the HCl concentration to zero, we now ignore its equilibrium expression any further. So we solve the problem as we did before. Eliminate OH minus in the charge balance equation by substitution from the water dissociation equilibrium. We have one equation and one unknown. We rearrange it, write it as a quadratic equation, and solve using the quadratic formula. We'll choose the plus square root solution because the charge balance equation tells us that the hydronium ion concentration will be a bit bigger than the formal acid concentration by the amount of hydroxide present. This is a very good approximation. Solving a quadratic equation is not that hard, but what about another approximation? When we solve this problem, when the formal acid concentration is 1 millimolar, the hydronium ion concentration is almost the same as the chloride concentration. If you look at the charge balance equation, this essentially is saying that the hydroxide is very small compared to the hydronium ion concentration. Our chemical intuition should be confirming this. In a solution with a strong acid, the hydronium mostly comes just from the acid dissociation itself. So the second approximation is this. And this approximation almost trivializes the problem. The concentration of H plus is just the formal acid concentration. End of problem. But we observed before that this approximation is not universally applicable. As the formal concentration decreases, the influence of the water dissociation increases, and it can finally dominate the strong acid's contribution. When does that become a problem? Well, here's a table showing the results of the quadratic solution versus the approximate solution for various formal acid concentrations. Also given is the percent error made by the second approximation. Notice that for concentrations greater than 1 micromolar, the error is less than 1%, but the error quickly grows to an unacceptable level at lower formal concentrations. Takeaway message: use the second approximation for formal acid concentrations greater than about 1 micromolar if a 1% error is acceptable, and if not, use a higher cutoff value. But below some level, you will need to use the quadratic solution. Next, let's look at a weak acid problem. We now had to consider both the equilibrium expressions. The full solution led to a cubic equation that was reasonably solvable. But we noticed something in the solution, namely that the hydronium ion concentration was essentially the same as the conjugate base form of the acid. Why is that? Well, it's really the same approximation as for the strong acid, namely that the vast majority of any hydronium ion that is present is a result of the acid dissociation and not the water autoionization. We make this approximation and can switch in H plus for A minus in the equations. We modify the mass balance equation and the acid equilibrium expression, solve for HA and substitute into the mass balance equation, and we find the quadratic expression that can be rewritten. The solution using the quadratic formula gives us this. Now, there are other kinds of approximations we can consider. Here's a different way of looking at the problem. What is it about this quadratic solution that is being neglected? Well, the obvious piece of data that is missing is anything about water. Kw is not found anywhere. And as we have found, when the hydronium being released by the action of the acid starts to be comparable to the hydronium arising from water's autodissociation, well, that's when the quadratic approximation begins to fail. What if instead of dropping the contribution from water, we examined what would happen when Ka becomes very small? Can we look just at the behavior of very weak acids? Well, look again at the cubic solution. If Ka is very small, then Ka times Kw must be very, very small, because we know that Kw is small already. That means we could ignore the final constant term. Our cubic now looks like this. Now we divide every term, including the 0, by h plus, and the equation now becomes quadratic. We can use the quadratic formula again here and see how this makes a small but meaningful adjustment to the quadratic equation we already use. We just add Kw times Cha term, Kw to the Ka-Cha term in the radical. This will indeed improve its mathematical behavior in the low H plus concentration range. But we are still looking for further simplifications that will nevertheless still have acceptable results. If Ka is very small, that means the acid is very weak, so the H plus concentration will be small too. Compare the formal acid concentration, Cha, to the H plus concentration. Under these conditions of a very weak acid, we can anticipate that KaH plus is much smaller than KaCHA, and we will assume that the KaH plus term is small enough to ignore. Our equation has now become very simple. And we bring up the constant term on the other side and solve for H plus. And this is our next approximation, which is for very weak acids, but still includes some contribution from water autodissociation. We have one final approximation to make. If we feel that the formal acid concentration is high enough that Kw is small compared to KaCHA, we obtain the simplest estimation of H plus concentration, just the square root of the product of the dissociation constant and the formal concentration. We now have two approximations using the quadratic formula and a further two approximations using just square root. We have four approximations to our cubic solution to the monopronic acid or base equilibrium problem. They're all based on comparing the magnitude of the formal concentration, CHA, the acid dissociation constant, Ka, the water dissociation constant, Kw, and various products and sums of these terms along with the anticipated hydronium ion concentration. How can we decide which one to use and when? Well, obviously, taking the square root of the product of KaCHA is much simpler than using an iterative numerical root finding routine in a cubic equation. But is it ever a good enough estimation? Well, look at these graphs to get some sense of where things can be used. The first graph is comparing the results of each of the four approximation equations to the cubic result for various values of the acid dissociation constant, Ka. The formal acid concentration is constant at 1 millimolar throughout. The cubic values are found using either GoalSeek in Excel or the roots function in MATLAB. The squiggly regions you see are, I believe, a result of numerical round-off error, so I don't think the trend is very useful. I think the trend is very useful, but just don't focus on these rapid changes. I don't think they're real. Here at the right edge, the graph has the largest value for Ka. This corresponds to the stronger weak acids. As we move to the left, we encounter increasingly weak acids. The y-axis has the log of the error between the cubic equation result and that for the corresponding approximate solution. This is calculated as the absolute value of the difference between the cubic and the approximate result, divided by the cubic result. A log value of 0 means that this ratio is 1, which means that the difference is as big as the value itself. This would be a 100% error. This would be bad. A value of -2 would correspond to a difference of about 1%. Not too bad. A value of -8, the difference is in the parts per billion range, not worth mentioning at all. But if the result is above 0, the approximation solution is really bad in this range. Here's the quadratic solution, which includes Kw. We can view this as the most complex approximate solution. It corresponds to the blue curve. For the strong weak acids, its error is in the parts per billion range. It is an excellent approximation. As the acid strength decreases, its error rises into the parts per million range, but it is always a very good approximation. When seeking about 3 or even 4 significant digit precision, this approximation works fine across the entire range of Ka. The other quadratic formula solution, the one leaving out the Kw, starts at the same place as the first quadratic formula solution, but leaving out the water does cause its error to rise more quickly. However, even when you reach Ka equal to 10 to minus 8, the error is still in the parts per thousand range, still quite acceptable. But at still lower values of Ka, the approximations begin to fail poorly. But for a considerable range of values, it performs admirably. Next, we consider the square root solution that includes Kw. For strong acids, this is a terrible approximation. But that makes sense because we obtained this result by expressly considering that Ka was small. We should not be surprised that it fails in this region. Its error drops as we go to weaker acids, as would be expected. And at the very weakest acids, its error is comparable to that of the very best quadratic formula solution, with errors in the parts per thousand range. Finally, we look at the most approximate solution. The math to implement it is very simple, but it too starts out very poorly for strong, weak acids. It mimics the behavior of the other square root solution, but when K gets into the 10 to the minus 8 range, its error starts to increase again, and it starts to follow the error pattern of the less complete quadratic formula solution. In the range 10 to the minus 7 to 10 to the minus 9, it produces an error of about 1%, which is not too bad, but it's not very good for all of the values above or below this range. What happens when the formal acid concentration is smaller than this? Well, this graph was created in the same manner as for the other graph, except that the formal concentration is 10 micromolar. Unsurprisingly, the observations and conclusions are similar. However, for the strong, weak acids, even the best quadratic formula has a greater error. It's still quite good in this case. Its error performance is pretty flat throughout the entire range. The other quadratic formula starts off equally good, but begins to fail below K 10 to the minus 7. The best square root solution starts off terrible again, an error of a factor of 50, but drops, and below 10 to the minus 8 has an error of 1% or better and ends up similar to the best quadratic formula result. The simplest version follows the other square root in the region where it performs poorly, and then starts to follow the simpler quadratic formula in the region where it performs poorly. So what lessons can we learn? Either quadratic solution works well for acids with strengths above 10 to the minus 7. The more complete version works well at still lower Ka values. The square root solution that includes Kw is useful for very weak acids with Ka below 10 to the minus 8, but do not use it for strong, weak acids. The simplest square root solution is seldom accurate. You may consider using it occasionally when you want a ballpark figure with a quick back-of-the-envelope calculation for the hydronium ion concentration, but generally speaking, you should be using a quadratic formula solution, and if you're going to that trouble, it just as well be the one that includes Kw. But the square root with Kw works very well for very weak acids. Another point to remember is that we do see that as CHA decreases, the error of even the best approximation is worsening. For very dilute solutions, only the cubic equation gives acceptable results. But then, if the solution is very dilute, the pH is approaching 7, and you would need the cubic if 3 or 4 decimal places are required, which is not very often the case.